My name is Bruno Desruelle. I'm working for EXAIL, where I am in charge of the strategy in photonics. EXAIL is in charge of developing an engineering model of the laser system that will be used for the trapping, the cooling, and the quantum manipulation of the rubidium atom. This is a key element of the instrument because it directly impacts the performance of the sensor, and this means that we have to face very stringent specifications in order to meet the very ambitious objectives of performance targeted in the CARIOQA PMP project. So this means that we need to develop a very complex laser system with several independent fibered outputs offering top-level performances in terms of phase noise, frequency stability and accuracy, spectral agility, all optical parameters basically. So that's a lot of work to make this happen, but that's also a very exciting challenge. It's true that we made an early start, and the decision to create a company with the objective to launch on the marketplace a quantum gravimeter was made at the end of 2009, so almost 15 years ago. Starting from that, it took us about 18 months to prepare the project, and Muquance was officially created in 2011. We were able to hire our first collaborators and start our R&D program in September 2011. Then it took us about 2 years in order to have our technologies work fine, and we had our first satisfactory signals delivered by our gravimeter prototype at the end of 2013. And at the same time we delivered our first laser systems. Then it took us another 2 years in order to develop the first serial unit of gravimeter that was delivered in 2015, and it was the beginning of the production of these instruments. I'd also like to mention 2016 because we reached break-even, and it was really for us the confirmation of the economic viability of our project. Then 2018 was also important because we delivered the first field versions of our quantum gravimeters, AQG B01 and B02. Then maybe I think we can mention 2021 with the merger of our company Muquance with IXBlue, because it was really the beginning of a new adventure. So many things to tell. As you can see, it's a rich story. The operating principle is at the same time very simple and highly complex. It's very simple because basically the measurement principle was inspired by Newton and his falling apple. So basically it's about taking a test mass, dropping it and measuring the vertical acceleration experienced by this free falling test mass. Where it gets complicated is that instead of using an apple, the test mass we're using is a cloud of laser-cooled atom down to a temperature close to the absolute zero. So we're talking of an extremely cold state of matters. And second, because we are exploiting the laws of quantum physics in order to perform this acceleration measurements. And more precisely, we are really exploiting the wave nature of the atoms in order to build an atom interferometer. And the plan is really to measure the atomic phase shifts between the two arms of the interferometer in order to determine gravity. Of course, operation of a quantum gravimeter in space obliges us to address some very specific questions. First, because we need to optimize the size, weight and power consumption of the laser system, and second, because the instrument will be exposed to very stressful environmental conditions. So this implies that we need to develop a laser system that will be as compact, as light and as power efficient as possible. And also this implies hardening our technologies in order to make sure that all the components and the global system will be able to withstand the levels of shocks and vibration, of radiation, the thermal stress to the payload will be exposed to in space. Clearly, yes, because there are many common features between a ground-based quantum gravimeter that needs to be operated in harsh environmental conditions such as the top of a volcano and the space quantum gravimeters. Both instruments need to be as small, as compact and power efficiently as possible, and in both cases we also need to have instruments that show a very high level of robustness. So clearly CARIOQA PMP is a great opportunity for us, and we are really convinced that the major part of the technological solution that will be developed in this project will be integrated eventually in our ground-based gravimeters. I really can't wait before we have achieved this.